Okay, so let's welcome our next speaker, which is Hiroyasu Tajima, on Gibbs-preserving operations requiring an infinite amount of quantum coherence.
Thank you very much for the kind introduction. First of all, I'd like to thank the organizers for giving me this very nice opportunity. This is my third time attending QIP, and every time I've learned so much from this amazing conference series. So I'm very happy to be a part of this exciting conference. The main topic of today's talk is the following question. Are the free operations in quantum thermodynamics really easy to implement? To answer to this question, we consider the coherence cost of Gibbs-preserving operations. To see why this question is important, let's revisit the basics of resource theory. In resource theory, free states are easily prepared states, and free operations are easily performed operations. Each resource theory is structured based on the choice of these two. And in quantum thermodynamics, free states are Gibbs states, and free operations are Gibbs-preserving operations or thermal operations. Namely, there are two candidates of class of free operations. And the structure of quantum thermodynamics strongly depends on which one is adopted. So, clarifying the difference between these two Gibbs-preserving operations and thermal operations is crucial. And the main message of today's talk is that some Gibbs-preserving operations require infinite amount of coherence cost, and thus they are physically infeasible. Before going to the details, I introduce my collaborators and papers related to this talk. The main paper of this talk is this paper, which is collaborated by Ryuji Takagi at the University of Tokyo. This paper is recently accepted by PLL, and the results in this paper are based on these two papers. The first paper is again collaborated by Ryuji and Yui Kuramochi, and the second paper is collaborated by Naoto Shiraishi and Keiji Saito. All of these papers are on the same topic, the resource cost of channel implementation under global symmetry. So all of these are related to resource theory or asymmetry. I really like this coherence resource cost topic, and since these three papers are accepted by QIP as talks, apparently QIP likes this topic as much as I do. Anyway, from now, this talk follows this outline. First, I explain about the background and brief summary of main results and setup and details of the results. After that, I give a very rough proof sketch. And in the end, I will summarize my talk. Let's see the background and brief summary of main results. Let us introduce the definitions of thermal operations and Gibbs-preserving operations. When a CPTP map is realizable with an extra Gibbs state and energy conserving unitary, the CPTP map is a thermal operation. And when a CPTP map preserves Gibbs state, then it is a Gibbs-preserving operation. The merits and demerits of these two classes are contrasting. The merit of thermal operations is that its implementation cost is clearly zero, because Gibbs state is a free state in quantum thermodynamics. And the demerit is it is difficult to analyze, because its definition is implicit one. And the merit of Gibbs-preserving operation is it is easy to analyze because of the simplicity of the definition. Because of this merit, recent important works in quantum thermodynamics employ Gibbs-preserving maps. However, the implementation cost of Gibbs-preserving operation is still unclear. So clarifying the coherence cost of Gibbs-preserving operation is crucial. About the cost, The first question is this. In the first place, are there really non-zero cost Gibbs-preserving operations? Unfortunately, the answer is yes. Some Gibbs-preserving operations require non-zero energetic coherence. This result is given by Feist, Oppenheim, and Renner, and they showed that there is a Gibbs-preserving operation lambda such that to realize lambda with using energy-preserving unitary, the extra state rho must not commute with the Hamiltonian. So rho must have an energetic coherence asymmetry. Therefore, some Gibbs-preserving operations require non-zero energetic coherence. Then there is next question. How much coherence do we need? More precisely, the question is, to realize an arbitrary Gibbs-preserving operation lambda with using energy-preserving unitary, how much coherence is required in the extra state? This question is important because of two reasons. First, it is related to the resource theoretic difficulty of implementing Gibbs-preserving operations. Indeed, it is selected as an open problem in quantum thermodynamics. Second, it is related to the possibility of infeasible Gibbs-preserving operations. Namely, if there are Gibbs-preserving operations requiring infinite coherence cost, they are infeasible. The second point is also related to no-go theorems for quantum information processing under global symmetry. Let's see about that. Under global symmetry, several kinds of channels are prohibited due to their infinite implementation cost. For example, Wigner-Araki-Yanase theorem and unitary Wigner-Araki-Yanase theorem prohibits measurements and unitary gates which do not commute with conserved charge. And Eastin-Nil theorem also prohibits covariant codes with perfect recovery. So, if there is a similar trade-off relation for Gibbs-preserving operations, it prohibits some subclass of Gibbs-preserving operations. Now I summarize my questions and show the main results. The question is, are there physically infeasible Gibbs-preserving operations? In other words, are there infeasible free operations? The answer is yes. Some Gibbs-preserving operations require infinite amount of energetic coherence, and thus they are physically infeasible. And there are 2 points related to this answer. There exists an infinite number of such cost-diverging Gibbs-preserving operations. And there are tuples of quantum states such that the transformation from rho to sigma is possible only by cost-diverging Gibbs-preserving operations, but impossible by finite cost Gibbs-preserving operations. So limiting free operations to Gibbs-preserving operations with finite threshold on resource cost changes the theoretical structure of quantum thermodynamics. To derive this result, we use the trade-off relation in this paper. The trade-off between irreversibility and coherence cost for arbitrary quantum channels. This trade-off unifies and extends these Wigner-Araki-Yanase type theorems. And the main result of this talk is also derived from this result. So we can say this result is a Wigner-Araki-Yanase type theorem for Gibbs-preserving operations. Next, let's see the details of the main results. We first introduce our setup. We consider a Gibbs-preserving operation from A to A prime and its implementation with Gibbs-preserving unitary. The goal is to evaluate the coherence cost of lambda, which is the minimal sufficient amount of coherence in rho b here, to realize this a target quantum operation. In the next 2 slides, we define the measure of coherence and the coherence cost. As the measure of energetic coherence, we employ the SLD quantum Fisher information for this state family. The formal definition is this. This quantity is the standard measure of energetic coherence in the sense of resource theory, namely resource theory of asymmetry. And this is also a standard measure of quantum fluctuation of Hamiltonian H. F low H is 4 times minimum average of variance of H. Here, Qj and psi j is the decomposition of rho, which is not necessarily as orthogonal one. And next, we define the coherence cost of quantum channels. Here, we define not only the cost of zero-error implementation, but also the cost of approximate implementation. To do so, we say this tuple realizes the target channel within error epsilon when U and rho B realize lambda within error epsilon, and U satisfies the conservation law. Here, we use the gate purified distance to define the error epsilon. And the purified distance is this, and this F is Ullmann's fidelity. And we define the cost of approximate channel implementation as the minimum quantum Fisher information contained by rho B in the tuple which realizes lambda within error epsilon. By definition, the case of epsilon is equal to 0 is the implementation cost without error. Now we introduce our main results. Our results are divided into 3 theorems. The first theorem is this. If system A and A prime satisfies this condition, there exists a cost-diverging Gibbs-preserving operation from A to A prime. This condition is easily satisfied. To see that, let's see the case of HA is equal to HA prime. In this case, the condition is equivalent to the condition of energy eigenvalues. Then, for example, in the case of non-degenerate 3-level Hamiltonian, this inequality clearly holds because this EA3 here is strictly larger than EA prime 2 here, and EA prime 2 is strictly larger than EA1 here. So this inequality holds, and there is cost-diverging Gibbs-preserving operation. The same discussion is valid even for more larger system. Indeed, whenever HA is equal to HA prime and they have at least 3 different eigenvalues, then there are cost-diverging Gibbs-preserving operations from A to A prime. Furthermore, we can show that even for 2-level systems, when energy gap of the initial Hamiltonian is larger than that of final Hamiltonian, this condition holds, and thus there is a cost-diverging Gibbs-preserving operation. So there is a cost-diverging Gibbs-preserving operation even on a qubit system. From these 2 examples, we can see that the cost-diverging Gibbs-preserving operations are a very common one. So they exist between almost arbitrary systems. Next, we explain theorem 2. Theorem 2 is about state transition. When system A and A prime satisfy the same condition as theorem 1, there exists rho on A and sigma on A prime such that the transition from rho to sigma can be realized only by a cost-diverging Gibbs-preserving operations. Again, the condition is easily satisfied, and thus there are infeasible state transition between almost arbitrary A and A prime. We also find an upper bound and lower bound for cost of approximate implementation of the cost-diverging Gibbs-preserving operations. This is the inequality. As shown in this equality, the costs of approximate implementation are inversely proportional to the error of implementation. Here, epsilon is error, and C and A are constants. The lower bound is derived from this result, and the upper bound is derived from this result. And from this inequality, we obtain the scaling like this. Here, n is the system size. We can also show that this scaling is the worst in the most in all approximate implementation of all CPTP maps. So we can say that Gibbs-preserving operations include the most costly class in all CPTP maps. Next, we show a very rough proof sketch of theorem 1. As I explained, theorem 1 is corollary of this trade-off relation. Here, we show the strategy of the derivation of this result. So I show this line. The trade-off relation is this inequality. The setup is we consider an arbitrary CPTP map and its implementation with using energy conservation. Then this inequality holds. In this inequality, this term delta is the irreversibility of the channel, this channel, for test ensemble omega. Here, psi and phi are orthogonal pure states, arbitrary orthogonal pure states. And the definition is the formal definition is this. So this is average, minimum average recovery error, where R runs runs over all CPTP maps from A prime to A as recovery maps. And the term C is the change of the energy by this channel. The definition is this, and gamma dagger is dual of gamma. And large delta is a positive constant. This trade-off relation predicts that the coherence cost of arbitrary CPTP map is inversely proportional to its irreversibility. Therefore, if we can find a Gibbs-preserving operation satisfying C here is strictly larger than 0 and delta is equal to 0, then this term diverges, so the cost also diverges. And we give a method to construct such Gibbs-preserving operations. The strategy is as follows. Sorry. We focus on the fact that when a channel gamma maps orthogonal pure state psi and phi to orthogonal states, then the irreversibility delta equal to 0 for this test ensemble. So a measurement and prepare channel is a good candidate. Measurement prepare channel satisfying this is a good candidate. And in this measurement and prepare channel, when these two conditions hold, C is strictly larger than 0. And many measurement and prepare channels can be written as Gibbs-preserving operation. So it looks good strategy that we construct such measurement and prepare channel as Gibbs-preserving operation. Indeed, we can construct such measurement and prepare channel as Gibbs-preserving operation. Let's see an example. We give this an example. This is just an example, so we can consider more general case, but in this talk, we focus on this example. We consider a 4-level system which has 2 degenerated ground states. For this system, this channel, this measurement and prepare channel, is the channel that we seek. Here, Pj and P plus and P minus are projections to psi plus and psi minus. And this term is an additional term which makes the channel gamma Gibbs-preserving. By definition, this channel maps psi plus to 0 and psi minus to 0b. Sorry, psi plus to 0a and psi minus to 0b. Therefore, this and this hold, and thus gamma is cost diverging. And by definition, gamma maps Gibbs state to Gibbs state. Therefore, it is Gibbs preserving, and thus gamma is an example of cost diverging Gibbs preserving operation. That is the proof sketch. Now I summarize my talk. Some Gibbs preserving operations require infinite coherence cost. Therefore, such Gibbs preserving operations are physically infeasible. And this is an application of a trade-off relation given in this paper, which is a trade-off between the coherence cost and irreversibility of arbitrary CPTP maps. And there are tuples of sigma and rho and sigma such that the transformation from rho to sigma is possible only by cost diverging Gibbs preserving operation. So limiting free operations to resource restricted Gibbs preserving operations changes theoretical structure of quantum thermodynamics. Therefore, caution is required when we use Gibbs preserving operations in quantum thermodynamics and other related fields. Now I finish my talk. Thank you very much.
Thank you for the very nice talk. Any questions? Yeah, we have some.
Okay. Yeah, is this on? Yeah. Okay. Thanks for the great talk and the very nice results. I was just. Can you remind me? You bound this quantum Fisher information as a measure of coherence. Can you remind me how this is related to, say, the size of a reference frame that I would need in some, in some operational setting to implement the map?
So the amount of quantum Fisher information is bounded by the size of the reference frame. So our bound can be used to derive the limitation of the size of.
Right, and that would be the dimension of the reference frame.
Yes, exactly. So, for example, when the reference frame constructs some qubit system, then the number of qubit is can be bound.
Right. Thanks. My second question was I was curious about your thoughts about this, because I thought a bit about I was always worried by how these frameworks they depend a lot on the framework you choose, right, and how you set the rules, and it's depending, and it's sometimes I find it. I'm worried that we're being too strict in requiring that operations, you're not allowed any type of coherence, because if you think about how you address qubits in a lab, you send coherent pulses on them. Somehow coherence seems to be somehow available in one way or another. And then there are other settings. There's another thing that was kind of weird in the context of this Gibbs-preserving operation that, that's not a thermal operation, is if you tweak the definition of a thermal operation and cheat a bit and just say that I'm allowed to do any energy-preserving unitary and trace out a system, and then but you trace out a system that might not, where the Hamiltonian might still be interacting with the thing that you're tracing out. If you do that, then it turns out that the map that is Gibbs-preserving but not thermal operation, it turns out that you can actually write it as a thermal operation in this tweaked kind of cheating setting. So I was wondering how much you've thought about these kind of ways of circumventing traditional definitions of coherence and setting for thermodynamics, and kind of how robust I should think of this type of results.
Sorry, your question is now beyond my listening skill. But maybe the problem is the initial and final Hamiltonians are different. Is it right? No.
Well, it's subtler than that, but I suggest we chat.
Okay. Sorry.
Yeah. Thanks for the great talk.
Thank you for the talk. So my question is, have you explored other constructions of these channels besides just measure and prepare, or is this?
So infinite cost.
Yes.
Maybe there is, because our result is just say if C is strictly larger than 0, t is strictly larger than 0, and the irreversibility is strictly 0, then the cost diverges. So maybe there is other case other than measurement and prepare channel.
Okay.
Yeah, but now I don't find about the other example.
Thank you.
Thanks a lot for the very clear talk. I was wondering, when you say that it becomes infeasible to, say, do these operations, can you say something about the size of the circuit that you would need to implement this blow up, or
No,
some...
no, indeed. So asymmetry, quantum Fisher information, is fluctuation of energy. So when we try to implement such Gibbs-preserving operation, then we need infinite amount of energy. That is the restriction. That is not restriction on complexity. Yeah.
I see. And maybe the second question I had was, in one of your slides, you have this that if you have a Gibbs state as an input to the unitary, that has zero cost. Is that an assumption in the model, or because I can think, there are some Gibbs state are hard to prepare.
Maybe you talk about the first slide about summer operation. No.
That's right. So in the first slide, you had
that is assumption of the quantum thermodynamics. In quantum thermodynamics, Gibbs state is free state, so we can prepare that freely.
Right, but sometimes you can't prepare a Gibbs state efficiently. Is that kind of do people think about these things?
Yes. So sometimes it is difficult to prepare Gibbs state, but that is how to say another problem. Another problem than to resource theory of thermodynamics. So that is another question.
Okay.
Yeah.
Okay. Thanks a lot.
Maybe the final question here in front.
Very interesting result. So I was just wondering if you've looked at the asymptotic cost of Gibbs-preserving channels?
Yeah, that is a good question, and indeed, I don't know. So asymptotic cost. Yeah, so that is a good question. So the coherence cost diverges, but that is the single shot case. In asymptotic case, maybe the cost will be sublinear, but I don't know. Yeah, that is a good question.
And let's thank the speaker again. Thanks.